So now we're going to be looking at elastic collisions, and specifically the calculations involved in elastic collisions. So first of all, we should know by now the difference between elastic collisions and inelastic collisions, and the difference is elastic collisions, kinetic energy is conserved. So if we have a 200-gram pool ball moving left, colliding with a 250-gram pool ball, I know all pool balls should be the same mass, but let's just assume they're different masses just to make the question a little more interesting. Determine the final velocity of each ball. So first of all, I'm just going to draw a quick sketch. We have this ball here, which is 250 grams, and that's moving to the right at 3 meters per second. And we have another ball, which is a little bit less massive, 200 grams, moving to the left at 4 meters per second. So the question is, these things are going to collide and bounce off each other. What's the final velocity of each ball going to be? So it's not going to be like an inelastic case where they stick together at the end. They're going to basically bounce off each other and both be moving at final speeds that are, well, we don't know what they are. And that's the whole point here. So how do we solve this problem? Well, we know that the conservation of momentum always applies in the case of colliding things. So we know we can call this M1 V1 plus M2 V2 is going to equal the final momentums, right? Now I'm actually going to change the notation a little bit than the one we were using before. I'm going to call this V1I and V2I for the initial velocities. And then M1 V1F plus M2 V2F. And remember, these velocities are vectors. That is important. So let's plug in what we know. And also, I'm also going to define right as being the positive direction, because that makes sense. So let's plug everything into the equation, everything that we know. So we know 250 grams times V1, which is 3 meters per second in the positive direction, plus M2, which is 200 grams times negative 4 meters per second, right? Because it's to the left, it's in the opposite direction. And this is going to equal the mass 1, so 250. I should label this. This is M1 and this is M2. 250 times V1F, which we don't know, plus 200 V2F, which we don't know. So, I mean, we could simplify this on the left side. We can put all those numbers in. Notice, by the way, that I left it all in grams instead of converting to kilograms, and that's because we're going to have kilograms here, kilograms here, kilograms here, or grams there, grams there, grams there. Either way, it doesn't matter what the unit is. Those units are going to cancel out with each other. Like if I divided everything by kilograms, it would cancel out, and here, right? It would cancel out of all 4 things, so you don't really need to worry about what unit you use for mass as long as it's the same as it's the same for all of them. So anyways, we know that. So this equation, the problem with this equation though is that it has 2 unknowns, right? We can't solve for 2 unknowns when we have 1 equation. So what we could do is we could invoke what we know about elastic collisions, and that is that the kinetic energy is also conserved. Not just the momentum is conserved, the kinetic energy is also conserved. So if we think about it, what that means is that we have our initial kinetic energy, and remember our kinetic energy is 1/2 mv squared, right? So if that's the case, let's look at that, right? So we have each object has its own kinetic energy before the collision, and each object will have its own kinetic energy after the collision. So we can look at this as 1/2 m1 v1I squared, right? That's the kinetic energy of mass 1, plus 1/2 m2 v2 initial squared. So that's our initial kinetic energy of both of our things. That's going to equal 1/2 m1 v1 final squared plus 1/2 m2 v2 final, right? Squared. So that equation is also going to be true. Now you might notice right off the bat we can divide everything by 1/2 to get rid of these 1/2s. And we have a simpler equation. And we could, again, plug in what we know. So we know mass 1. What was mass 1? 250. So this is going to be 250. The V1 is, what was it, 3, plus M2, which was 200, times 4 squared equals 250 times V1F squared plus 200 V2F squared. So that's another equation with two unknowns still. Now, both of these equations are going to be true, right? They're both going to be true. So now that we have two true equations, we should be able to do some algebra and solve for V1F and V2F, right? You're going to need to do some substitution or some elimination, and then it turns out you're going to get a quadratic at the end, so you probably can't factor it, so you're probably going to have to use the quadratic formula. It's a lot of work. So I'm actually not going to ask you to do that. If you want to try to do that just as an exercise, like a math exercise, you can. But since this isn't a math course, it's a physics course, I'm going to give you a bit of a shortcut. And the shortcut is this, down below at the bottom of the page. So you can actually plug everything in and simplify the equations. Instead of doing the quadratic formula and stuff like that, you can simplify it so that our final velocity can be calculated with this, our final velocity of object 1, and our final velocity of object 2 can be calculated with this equation. So they're just equations that you literally just plug in the values that you know, including the initial velocities and the masses, and you can find the final velocity of object 1 and the final velocity of object 2. So the equations, the hardest part about the equation is just making sure you plug in things in the right spot, keep track, make it very clear what your M1 and M2 are, and see if you get the right answer. So I'm not going to do the whole calculation here because it's super long, but I want you to try. See if you can get V1F and V2F. Now, you'll notice they called it VF2 instead of V2F. Doesn't matter. Either way, V2F, VF2, I'm okay with either way. I prefer to put the name of it first and then the final or initial. It's just this is the way that your textbook has it written out. One thing to keep in mind for this is a vector. These velocities are vectors. They're vectors, not velocities, not speeds. So make sure when you're putting these in, you take into account the positive direction, okay? So pause the video here, try it now, see if you can come up with the values for V1F and V2F. So when I did that calculation, barring any mistakes that I may have made, this is what I get, that the final speed or velocity of V1, so this ball here, is 3.22 meters per second in the negative direction, which is to the left, right? So we could rewrite that as 3.22 meters per second left. Does that make sense? That it started by going off to the right and ends up going left? It does, right? Because, it's bouncing off the other ball. And then for the final velocity of ball 2, it ends up being a positive direction. So this would be to the right, which also makes sense that this one bounces off going this way. This one ends up with a larger speed at the end too, which also sort of makes sense if you think about it because it's lighter, right? So it's going to it might end up getting shot sort of off the collision at a faster speed. That won't always happen, but it does make sense that it happens here. So there we go. Without doing all this crazy algebra between these two equations, you can just use these equations, and it's sort of just boring. You just plug them into the equation and it spits out the answers, but they are very useful equations for that reason. There you go.